All right, hi you guys. We are in week 12 and we are working on multiple regression. And this is the probably the culmination of this course is talking about multiple regression. You guys have arrived. This is probably where I was really excited when I was taking statistics because a lot of the pieces come together here and you're able to do a lot of inferences using, or make a lot of inferences using multiple regression about your data. So I already have the data set open in Jamovi. We're using the same data set that we did last time, album sales. We can go ahead and look at all the variables this time. We still have our adverts, our advertising budget, which is continuous variable. Sales, our album sales, which is a continuous variable. Airtime, the number of plays on radio, which is a count. So 0 means 0, that's going to be ratio level of measurement continuous. And image, band image rating, 0 to 10. Normally I'd probably call this ordinal, but for this example, leaving it as continuous is fine. So as always, we would go into our descriptive statistics, and these are all continuous variables. So we're going to get means and standard deviations for all of them. We're also going to look at our skewness and Shapiro-Wilk for normality tests to see how we are with our normality assumptions. And because this is your continuous, we're going to look at histograms and box plots. And we can see that our Shapiro-Wilk test, adverts and sales are significant, meaning they're not normally distributed according to the Shapiro-Wilk test. And our new variables, airplay is not significant, but image is. But like normal, I like to look at the skewness divided by standard error of the skewness, because the Shapiro-Wilk and the Kolmogorov-Smirnov can be a little strict on normality and are also affected by kurtosis, which is not quite so important when it comes to our normality assumptions. So adverts, skewness divided by standard error of the skewness is definitely greater than 2. Sales divided by standard skewness divided by standard error, not greater than 2, so we're not so worried about that one. Same thing with airplay and image, 1.29 divided by 0.17, that's definitely going to be greater than 2. So if we go down and look at our plots, just on our descriptives, we know we don't have any missing data, and values look reasonable in there. There's nothing extreme. So not surprisingly, our adverts plot we can see is positively skewed with outliers to the right. There's some outliers in our box plot there. Some deviation from our normal line looking at our QQ plot. So we expect all those. Sales looks a little better for normality, and no outliers in the box plot. And as we saw last week, those data points follow that normal line a little better. Airplay looks more normal. There is one outlier on the upper side, but that follows the normal line in the QQ plot pretty well. And image, we are skewed to the left, negatively skewed. Definitely some outliers down low, and not surprising to see those in the box plot. And they're clustered around the normal line except at the tails, so not too surprised to see that. Okay, so before we run a multiple regression, we want to look at some things. And the first thing we're going to do is run our correlation matrix. And we get to that by going to regression and Pearson correlation and correlation matrix. I've already run it. We're going to move all of our variables over here to the right-hand side. We're getting the Pearson correlation. We want to flag our correlations. And we're going to go ahead and get plots with densities and statistics. And we're going to look at these. And we're still looking for our linear relationship like we did last time. So we're going to look at each of our variables correlated with sales. And we can, this is where it's important to look at the plots. If you recall, you can have the same correlation, Pearson R, and have some very strange relationships. So you want to look at these. And here, when we look at sales with advertisements, we have a pretty much linear relationship. And sales with airplay, that looks pretty linear. And sales with imaging, although you can see, so those all look pretty good. We're okay with our linear relationship. The next thing that we're going to look at, since we have multiple predictor variables, is we're looking for something called multicollinearity. And ideally what we want is we want predictor variables that are related to the outcome variable, but not strongly related to each other. If their predictor variables are strongly related to each other, then that causes us a problem. And so we're going to look at our other correlations between our other variables. So if we look at adverts with airplay, we can see that that's not very strong. Same thing with adverts and image, and the same thing with airplay and image. So from the plots, we can see they're not very big. If we go actually look at the correlation matrix, we can see that 0.102, 0.081, and image and airplay 0.182, those are all low correlations. So we don't have a problem. And you might be wondering, well, what is the cutoff point? And a general guideline that I've seen in other texts is a strong correlation, which is 0.8 or above. And if you have predictor variables which have a strong correlation of 0.8 or above, then you might wonder, well, what should you do about that? And the answer is you need to make a decision of which of those variables you're going to take out of the regression. If you leave them in, they're going to cause a problem with some of the numbers that you're going to get as a result. And so you really should remove one. And really that comes down to what are you studying and what are your predictor variables and how theoretically important are they. And you just have to kind of make a choice based on those things. So there's really no cut and dried answer of how to pick a variable, but that are some things to consider. In our case, we're definitely okay. None of our predictors are highly correlated with each other, and we definitely have some moderate correlations with our outcome variables. So we look good when it comes to that. And then we can run our regression. And again, we got to that by going to regression and linear regression. And I've already got that loaded up. We're going to do sales in our dependent variable box. And these are all continuous. So our three predictive variables are going to go in our covariates box. And this week we're going to just leave this blocks alone. This automatically put our 3 variables into this blocks, and we'll talk some more next week about some other ways that we can do that, but that's good for now. So reference levels is for if you have a categorical variable or more than one. And I have given you some optional videos you can watch on dummy coding with regression. And this was one of the things that I thought was the coolest thing about regression, is that your predictor variable can be any level of measurement. So nominal, ordinal, interval, ratio, all of those levels of measurement can be predictors in regression. And your categorical variables, nominal and ordinal, dummy coding is what you would need to do to use that type of variable. And because of everything going on, I'm not going to get too much into it, but it was one of the coolest parts of regression that I really liked, and you guys can look at those videos and do some more reading on your own if you want to play with that a little bit. In fact, I would encourage it that you could go back to some of the analyses that we did earlier this semester with our independent t-test and our ANOVA, and you could actually do those tests using a regression model and get pretty much the same results. So, but we're not going to go into that and try it now. It's maybe something you can try on your own, and you can hit me up if you have questions. This time we're going to get some more of our assumption checks, or some collinearity statistics, our normality tests, and residual plots, and this thing called Cook's distance. We're going to talk a little bit about what those mean. And we're going to get our same model fit statistics, our R squared, and this time adjusted R squared, and the overall model F test. And I'm going to go ahead and let's look at this omnibus test on the ANOVA, and we can talk a little bit about it. We have our confidence intervals for our estimates and our standardized estimates. We're going to go ahead and get the standardized estimate and confidence interval. You want to check those boxes. So now that we've checked all that, we can come over and go through some of our results. So again, I would remind you, when it comes to regression, you really want to think about regression in 2 parts. And the first part is information related to the model overall, and the second part is information related to the parts of the model. So in my mind, I always divide those up, and any type of regression that you do, you're going to have those 2 parts. We have simple regression, where we looked at that. Now we have multiple regression, where we're going to look at that. In 2 weeks, we're going to look at another type of regression called logistic regression. And I'm going to go ahead and cover that in this class. It's a little more advanced because it's a nonlinear regression. But since we're all dealing in medicine and we're all in informatics, logistic regression is used everywhere in medicine. And it's also the foundation for, it's kind of the baseline for a lot of machine learning things. A logistic regression is making a prediction between 2 categories. Our outcome variable is a dichotomous variable, and so it's just a really good thing to be exposed to. But even this more advanced regression, we're still going to have the two main parts that deal with the model overall, and parts that deal with the parts of the model. And so I know there's a lot to remember with regression, but take it 1 part at a time, and it's a lot easier. So let's look at our model overall. So if you remember, for our model overall, and let's look at it on our menu and our output here, we have our model fit, and we have our R, R squared, and adjusted R squared. So we talked about big R and big R squared. And our Pearson correlation was our relationship between two variables, and that was our Pearson R, and it's lowercase r. Here in linear regression, we get this uppercase R, this big R, and it's very similar to a Pearson correlation, except this is the relationship between the predictor variables as a unit and the outcome variable. So if we look at our big R, 0.815, and we went back and looked at our Pearson correlations, you'll see that our big R does not match any of our individual correlations, and that's because big R is looking at how they function as a unit. If you recall last week where we did a simple regression and we only had one predictor for the outcome variable, and that big R matched exactly our little r, and that was because we only had one variable, and so that relationship was exactly the same as what it would be with just a little r Pearson correlation. But now that we have multiple predictor variables, that big R just isn't going to match any one of the correlations because they're going to function as a unit for this big R. The big R squared, also called the coefficient of determination, and you'll see that this is higher than it was last time, and that's not surprising because now we are including more predictor variables, and we should be able to predict more of the variance in the outcome variable, and we do. So the one downside is that the more predictors we add, this R squared can get inflated. So when it comes to interpreting our big R squared, I always use an adjusted R squared when I have 3 or more predictors. And you'll see with only 3 predictors, we go from 66.5% down to 66.0. It's not a big difference, but you'll see bigger differences when you have regressions that have more predictor variables. So in this case, I would say that our predictor variables share 66% of the variance with the outcome variable, or 66% of the variance in our outcome variable is explained by our predictor variables. So the adjusted R squared is probably one of those important model overall type of things, and explaining 66% of the variance in something is pretty good. I mean, that's over half. So you have done a good job picking some predictors to explain what's going on in your outcome. And so that's an important thing to look at. And then we also have an overall model test, an F test, which we looked at before. And this basically, if you remember, it's looking at what this is testing against is how does our model with the variables compare to a model with no predictor variables, just the intercept. And in this case, hopefully we're doing better when we include variables in the model. And as we can see, the p-value is less than 0.001. We're going to reject the null that the two models are the same. We're going to say that our model with the predictor variables is significantly different. And as we can see, has a large coefficient of determination, and so we have a decent model, pretty much. So now we're going to look at the parts of the model. So we've looked at our overall test with our F test and our big R and big R squared. Now we're going to look at the individual parts of the model. And sometimes a research question is focused more on the model overall, and sometimes the research question is focused more on the parts of the model, and it just really depends on what somebody is studying. But these are a couple of the different ways you can go. So this omnibus test, this is a little different for me because I've always used SPSS in the past, and I have not seen this particular piece of output. and I'm not really sure what this really tells us. You'll notice that we have an ANOVA table here, and we have each of our predictor variables and the residuals with sums of squares and degrees of freedom and mean squares, and we have an F for each one. And I'm not really 100% sure what this gives us over and above our model coefficients table. This is what I'm used to looking at, is the model coefficients table. If you went ahead and did the math and you looked at adverts here, and we have an F value of 150.3, if we look at our adverts on our model coefficients, we have a t value of 12.26. If you want to get out your calculator and try it, if you square 12.26, it will equal about 150.3. Same thing with airplay. If you square the t value of 12.12, it will equal our f value of 147. They're pretty much telling us the same thing. If you notice, the p-values on all three of those are exactly the same. Same thing on image. If you square the t value of 4.55, you're going to get our f value of 20.7. So it's pretty much giving us the same information that's in the model coefficients table, and I'm not really sure why they would include this omnibus ANOVA test like that, but they did, and there's a pattern that I noticed too about it, and maybe I missed something in the reading, and I'll try to read a little closer maybe in the future, but maybe if you catch something, you can explain it to the rest of us. So we're going to move on from the omnibus test and go down to the model coefficients, and this is where we really care about it. And last week, if you recall, we just did a simple regression where we used advertising budget to predict sales. And if you look at the homework from before, you'll notice that the intercept and the advertising, these coefficients are a lot different than what they were before. Before, the intercept was 134 or something like that. Adverts was 0.09, but that's a big change in the intercept. And what's going on here is that these numbers are how much this variable, when you change the predictor variable by 1 unit, this is how much it will change the outcome variable. And the thing to remember, you always want to add on to the end of that statement, is when controlling for the other variables in the model. So you'll notice now that we added 2 additional predictors, our coefficients on our previous formula numbers change a lot. And so if you add another variable or you take one away, you have to recalculate the whole regression because it will change all of your numbers. And that's something really important to remember. You can't just go, oh, this, one variable doesn't seem to be so important, and you just take it out of the equation. No, you can't do that. You have to go recalculate the whole regression because it will change all the coefficients. And the math for these is actually matrix algebra, and it gets pretty funky looking, but luckily we have computers to do that for us. So the thing to remember about these coefficients is these tell us how much a change in the predictor variable will change the outcome variable, and the thing to remember is when controlling for the other variables in the model. So with airplay, so a 1 unit increase in airplay will increase the outcome variable by 3.367 when controlling for the other variables in the model, or when holding the other variables constant. So that is something to look at. And if you remember, our non-standardized coefficients, which are this estimator column. This is the column that we use to make our prediction equation. So we could predict, if we knew what the advertising budget was, what the airplay counts were estimated to be, and what the image rating was, we could predict what our sales would be using this. And that would be the intercept, which is negative 26.6 plus 0.0849 times the advertising budget plus 3.3674 times the airplay plus 11.063 times the image. And that would give us our prediction equation for sales. So on our parts of the model, the first part of that is our unstandardized coefficients, and that really gives us our prediction equation. The other part of that is our standardized coefficients. So the thing about standardizing is, and the thing that's neat about it, is it takes the units away. So we really can't compare this number with advertising, with this airplay, with this image, because these are all in their own units. So advertising is in pounds, airplay is in number of times, image is in an image unit. That's like a psychological measure. And so these are apples and oranges. You cannot compare these directly with each other because they have their own units. But when we standardize things, like we do with the z-scores, when you standardize different things, you can compare different things even though they're different, because they all get changed to standard deviation units. And that's exactly what's going on with these standardized estimates. So now you'll notice that we can compare these numbers with each other, and we can see that advertising is 0.511, and airplay is 0.512, and image is 0.192. And what this tells us is that for a 1 standard deviation change in advertising, we're going to change sales by 0.511 standard deviations. For airplay, for a 0.512 standard deviation change in airplay, we're going to change sales by 0.512 standard deviations when controlling for the other variables in the model. And with image, for a 0.192, or for a 1 standard deviation change in image, we're going to change the sales variable by 0.192 standard deviations. So these are comparable, and so the biggest predictor is airplay, with adverts being really close, and image is the smallest predictor with 0.192, but it's still significant. So, and this is, you'll notice in the field book, this is one area where creating these regression models, I can tell that Jamovi is not quite as developed far along in their programming and what kinds of options and bells and whistles are available for the user. Right now it's a pretty straightforward, you say what variables are in the model, which we did over here. If you read the field text talking about SPSS, SPSS has some additional options. You can specify a set of variables, and then you can actually have the computer use some predetermined settings and either build the model one at a time. And if you have a set of variables and you're not sure which ones might be good predictors or not, you can tell SPSS to add one variable in at a time and calculate the model. And if one of the other ones looks like it's going to be significant, we'll add it in and recalculate the model, and it will do that. Or you can do the other way, where it will add variables in and then take them away one at a time until everything left in there is significant. And those are some of what they call forward and backward methods. But those have their place, and you should really be careful with them, because it can almost get to where people are making models and not really thinking about what it means. So While those things have their place, it's not a huge detriment in Jamovi to not have those kinds of things, because this really forces you to think about your model and what should be in there and shouldn't be in there. And in this situation where we have all of our predictors are significant, we really wouldn't make any change here. But if we did have a situation where one of them wasn't significant, we could go take that out and recalculate the model and see what we have. And there are times when you would want to take non-significant predictors out, and there are times when you might leave one in because maybe something is so theoretically important and there's been a lot of research and people always look at that if you took it out, people would criticize your analysis for not including something which they thought would be important. And so you might just leave it in, even though it's not significant, to show that you did include it, and that it was not significant in your particular study. But that this standardized beta coefficients are the other part of the parts of the model that we would look at. So we have looked at our model overall with our R-squared and our F statistics, and we have looked at our parts of the model, both the unstandardized and the standardized coefficients, the unstandardized for getting our prediction equation, and the standardized for comparing each of these variables with each other to be able to tell what's the biggest and what's the smallest. And I like this example because look at this. Image has a coefficient of 11.08, but the standardized estimate is a lot smaller. And here adverts is the raw coefficient is 0.08, a lot smaller than these others, and yet the standardized coefficient is big. The thing to remember with these non-standardized coefficients is you can totally change these numbers by changing the units that something is measured in. So, if maybe you measured something in feet and you change that to inches, then of course these raw coefficients, these unstandardized coefficients, are going to get a lot bigger because you just changed the units. And you didn't actually change anything. It's the same thing, but changing the units does change the raw coefficients. And that's something important to remember. Sometimes, if you have some really, really big or some really, really small numbers, that's an indicator that it might be wise to go change the units on the raw variables to make them to be some numbers that are a little easier to remember. Here we have, 1 or 2 digits with 2 or 3 decimal places. That's pretty easy for us to look at. But if these were like 6 or 7 decimal places, or if you had them huge and they were like six numbers, digits long, those numbers get big and hard to look at. So that's something to consider when how you measure something and what units you're going to use. So we have pretty much the same answer sheet that we did last time. Doing our data cleaning steps, looking for missing data and outliers. We definitely could consider doing some transformation on our variables that are not normally distributed with some outliers, but we're not going to worry about it here. In actuality, if I was really doing this analysis, I'd probably give it a try and see if it made things look a little more normally distributed. We looked at last week choosing the correct statistical test using our variables. We could go take a peek at that in Jamovi. We went into StatCat and relationships, and our sales is our dependent variable, and our other 3 variables went into here. We can see that we would do a linear regression analysis, and StatCat does give us a nice scatter plot for each of our variables here. We can see I have a pretty much linear relationship. And we'll talk a little more next week about some regression diagnostics. So I think I'm going to adjust the syllabus a little bit, and we're going to change next week's topic and focus a little more on some regression diagnostics. That's worth spending some extra time on, and we won't move from a different subject next week. So we're going to be kind of reviewing some of this information and looking at some additional things. So I hope you guys have a good week, and I will see you in office hours.